All right. How are you doing today? All right. Thank you for coming. I know there is a great competition from 1,000 different events in Bangkok. Is that working? Ooh, all right. So, let's talk about new things coming to Solidity. New things vLayer is bringing to Solidity. So we just opened vLayer as an open alpha 2 weeks ago. So it's kind of our first event, first time we're kind of going to communicate to the broader public. And yeah, today we're going to talk about all those goodies, all those new things you're going to be able to do from Solidity. So vLayer brings 4 new features to Solidity: time travel, teleport, web proofs, and email proofs. So not 1, not 2, not 3, but 4 new features. So before we go into those features, let me explain you the new execution model of Solidity that vLayer brings. So vLayer introduces 2 new types of smart contracts: provers and verifiers. For those of you who already been into ZK space, that's going to look very familiar. For those of you who may be in touch with blockchains like Mina or Aleo, that also might look very familiar. But the idea is very simple. We have a prover smart contract, which is like Solidity smart contract like any other. It inherits from prover-based smart contract, but unlike normal smart contract, it is executed off-chain. So it's not executed on-chain, it's not executed on layer 1, it's not executed on layer 2, but executed off-chain. And because it's not executed publicly on the blockchain, it can contain private inputs, meaning that you can put things into the computation that ain't going to be published on-chain. So that's a very nice property to have, as you're going to see, for those new superpowers that are accessible from prover smart contract. And here it is an example smart contract. Let's see if I can point. I can point. Can you see that? It's very small. All right. So this is a very simple smart contract. It inherits from prover, so it's prover. We're gonna prove that someone owned Bored Ape at the very beginning of the Bored Ape Yacht Club NFT moment. So it's a normal function. We call it main. Why not? We're gonna prove it for a specific owner and for a specific ape. So here's the first interesting thing: the ape. We're never gonna reveal on-chain what specific ape this person have. And we're gonna explain in a moment what this magical set chain ID is doing. But very simply, what happens here is we go back in time to this specific block, and in this specific block, we check whether this person was owner of this ape, and we return the owner as a result. There's also this magical proof, but there's nothing to do here. We're just returning the proof of the computation. That's going to be required for the verifier. All right? And which brings us to verifier contract. Verifier contract, well, it inherits from verifier. And it runs on-chain, so it can run on L2 or L1. And it takes the result of the prover computations, can verify the proof, and execute whatever it wants on-chain based on that. Right, so here is a verifier. It inherits from verifier. It has this one extra parameter called proof here, and also the address of the owner. So I'm just gonna go 2 slides back. This is exactly the same things, exactly the same types as we return here. Nothing extra to do, no recoding of the data or anything. And it has this new only verified modifier, which has an address of the prover and the selector of the function. So any contract we can deploy on chain, it can serve as a prover. We don't execute those provers on chain. We just use deploy them on chain to serve as a source of truth. And then, based on the fact that this guy owns a monkey or an ape, we can now do an action. For example, do a token airdrop for that person. Does that make sense so far? Easy peasy. All right. So now the superpowers comes in. So what is the stuff we can do with a prover that we couldn't do with other smart contracts all in one? Well, first thing you already seen a sneak peek of. You can interact with the historical state of the chain. You can do it with the set block method. So you can just set block to arbitrary block in the past on a given chain. And the following function called Solidity will execute in the context of that chain, of that specific block, specific state of the blockchain, and even specific hard fork of the blockchain. Right? So for example, here is a very simple function. Let's say we want to prove that someone is a hodler. So we want to say, okay, he had some money back, 1 million blocks ago, and he still had a money 1 million minus 100,000 blocks ago, right? Or whatever is the reasonable amount of blocks we take as a sign of someone being holder, right? So we just set block, take the USDC balance of that person. We set another block, take the USDC balance of the person, and we can take the minimum from 2, assuming that would be the base amount that he was holding over that period of time. Yeah, here is a little bit more complex function. So this function allows you to calculate the average balance of an account over time, and a little bit more complex, but no new elements. We're just iterating over, starting with the starting block, ending with the ending block, iterate for using given step, and we just set block, and we just keep adding so that we can, at the end, we can return the average. Does that make sense? Easy peasy? Oh, there's already a first question. Yeah, I mean, that would be great if you ask questions. Let me grab another mic for you. It's exciting questions. Is it? I think it's off. You need to turn it on first. All right.
Mic check, audible. Yeah, so a few things actually. Similar to what Google BigQuery has an historical data outside available for historical data, right? Now, when we loop through the time, how much time is it going to take? Because based on the steps, it can be, I'm doing a few things. And what kind of contracts can I check? For example, can I check my Uniswap positions beyond a certain time, how much that computation will take? Because I'm seeing only token balance examples right now. So
yeah, exciting questions. So I'm starting with the last one. The last one was what kind of contracts can I query?
Yeah.
So you can query arbitrary contracts. It's doing the full EVM execution under the hood. So it even knows that EVM was a little bit different before this block and a little bit different after that block. So you can even query, like unusual precompiles or EVM codes that were all only available at some point of time. Yeah, and the
computation part.
Yeah, and so the computation time. So it's important to understand that this is all happening in zkVM. So all this execution that's gonna happen, and we're gonna put result on chain needs to be proven. So that's pretty slow. So we also just announced alpha, so it's much slower than it will be in the future. So it takes, let's say, for a simple proofs under half a minute to more complex about 3 minutes. We think we have order of magnitude improvement to be done in the long run, half an order of magnitude in the mid run, in the let's say in a quarter or two.
Yeah, because my understanding is I've seen subgraph, subquery, flipside also come up, and with subgraph we can do some aggregation in our own backend as well, right? Or we can do polling as well, that can come up. So I just want to understand that what would be the use case here, because there is one thing that is proof that okay, I'm getting this data 3 minutes ago, but what if I can have faster databases? People earlier were using Postgres, Snowflake as well.
Sure.
Try to speed them up.
Sure. So it's super important to understand that the value we're bringing here is you can use that stuff on chain. in a way that you don't need to trust us or you don't need to trust anyone. This is all cryptographically proven, so that this data you're bringing is permissionless. So we can think about it as an extension to the standard execution model of Solidity, versus there's the graph and many other solutions you can use, indexers, but those are not giving you trusted data, so you don't want to.
What if I can get to a trusted oracle? Because I'll give you an example in DeFi, right? You use chainlink oracles, but you have to trust the chainlink algorithm itself.
Exactly.
And many people do actually, right?
Exactly.
Because they take few set parameters that this is the volume on certain sexes that then only will allow certain things. But most of the DeFi underlying uses oracles. Now, oracle is a concept you have to trust the party itself, right? That because Chainlink is deriving that price, they're just telling us how they're doing it. They're publishing a proof also a similar way, but they have their own algorithm to list people, and then you get a certain price. Is it not a better solution to have, because that will require so much less technology? Because this will be very computationally expensive over time. Whereas if I have that data, I can just oracally run, and then I can just have the state.
It's a very fair question. I think it's very fundamental to blockchain itself that we build permissionless applications. It's great that we have all the things we have from Chainlink, and whatever other Oracle system. But the problem is, what happens if they fail, or what happens if they disappear, or what happens if they make a mistake, right? So this is bringing the latest cryptography and allowing an execution in a way that you don't need to trust us, you don't need to worry that we disappear, because this is all built from cryptographic primitives that proves the correctness of the computation.
Yeah, but timing will be an issue. Maybe I can take it later.
Yeah. So this blockchain thing, it's kind of slow and expensive. If you want to run your computation on the blockchain, you should really consider it slow and expensive. Then you should really consider just using the cloud instead of Ethereum.
Yeah, but that's the concept of L2s, right? That's how L2s, L3 came. They did some of the things off chain, then put it. If you see Merkle rewards and others, now GameFi is coming. The transactions needs to be much faster.
It's all coming. It's gonna be much. I mean, another thing. So first thing is, like, you should really deeply consider if you want to use blockchain, if you want it to make it fast. And the other thing is you should really consider is if you look at zero knowledge, and it already, I think it sped up 10 times over last year and another 10 times previous year. Like, it's 100 times faster, and we're not at the end of the curve yet, so it's going to be much faster. And it's now good time to start building on top of those just maturing technologies, so that you have those permission protocols, say, next year, working, and you can start building all the stuff you couldn't build before.
Yeah, maybe I'll say that.
Thank you. Ooh, that's a lot of questions for a warm-up. Yeah, but it's exciting times, and it's a 4 questions, because it's really important to understand those trade-offs, and understanding those trade-offs, there's a lot of trade-offs in the blockchain space and a lot of trade-offs in the ZK. Still, we should be pushing what's possible with permissionlessness and what should be possible to build. And I'm gonna talk a little bit more about use cases later and all the exciting things we're looking forward to build. Yeah, can we go back to slides? All right, thank you. All right then. So the second superpower, I want to answer your question one more time, because we're going to talk about teleport. So I'm going to talk about teleport and then compare it to centralized solutions. I think that's going to be for comparison. So teleport is very similar to time travel. It allows you to interact with multiple chains in a single call, so that you can aggregate the data from multiple different chains in one computation. And you do it with a very simple thing called setChain. So that's a function. And it has 2 arguments: chain ID we want to jump to, and block number we want to jump to. So similar in the time travel, we're going to work on historical blocks. And following function call after the setChain will execute in the contents on a different chain. Right? So here is an example piece of code. It allows you to calculate the balance of a person across the different chains. Right? So maybe you want to prove someone is a whale. So maybe we take his full net worth, which is spread across different networks, right? So we have set chain, we go to optimism, and to a specific block, we take the balance off, we jump to another chain, this time is, let's say it's base, we set it to specific block, we calculate that, we take the balance of the person on the chain, and we return the total. This is the real life function that allows you to calculate balance across different chains, and it allows you to just iterate over whatever is the list of chains and fetch their balances and return the total. So when it comes to teleport, I think it's worth mentioning, you don't need teleport. You can go and use bridging, or you can use external oracles. But then if you look at the list of the most hacked things in the history of the blockchain, like this over $500 million hacks, what do you find on the top? The bridges. So it was super important for the bridging to become permissionless. And that's why we believe a lot of L1s failed, and L2s are so such a fast-growing space because they have safe bridges, right? So we believe that the same thing needs to happen to the more general computation. We need to make smart contracts more powerful because they're very limited today. So just finishing on the question before.
How will it compare to an application like DeBank? DeBank does a similar thing for multi-chain assets. You get the portfolio and you get it over time. I'll just bring that question at the end again with the superpowers.
Yeah, let's park it and happy to discuss in detail. All right. So the next two superpowers I want to discuss are a little bit more complex. So I will start with examples. So we're going to talk about web proofs now. Web proof allows you to take data from the web and put it into a Solidity smart contract, parse it, and use it on-chain. So one example is real-world assets. So for example, imagine you want to issue a token that might be, gold, stable coin, that might be US treasury bonds, whatever else. So imagine if you want to issue more of the token as a manager of such a real-world asset, you need to first prove you have all those funds, right? So what you do with web proofs, you can go to your bank, you can fetch your balance from the bank, you can generate a proof, and then only after the proof is issued, you can actually mint tokens. Well, there are two things here to notice. First thing to notice here is, yeah, but that sounds like oracles all over again. Well, there is an important difference. This bank account stuff, this is your private data that is not available publicly, that you would need to fetch with oracles. And the second important difference is, and the second thing to note is that you say, okay, so I have $1 million on my account, I issue all those tokens, and then the money is gone, right? Well, that can be solved by routine checks that you can do on periodic basis, whether it's daily, weekly, monthly, and you can issue emergency liquidation of the protocol, for example, if the balance is out of whack. So real-world assets will never be fully permissionless, but we can bring them to trust minimized space, where today are they pretty far away from that. And another exciting example, and this was innovated by the great team from ZK-P2P, so is this Web2, Web3 markets. So you can build on-chain something, you can trade something in the off-chain world on-chain, right? So in the case of one of the first projects from ZK-P2P team, they built on-ramp, so you could trade crypto for fiat currency. And the way you would do that was very similar. You go into your on-ramp application, you get your, you send money to the person on the other side, you get to your bank, do all the stuff, generate a proof, and only after the proof is generated, you can claim back crypto. All right, so here is an example code. So this specific piece of code, it's proving, it allows you to prove that you have specific Twitter handle, right? So it takes a web page, it verifies the web page is coming from this address, and in this address, and you need to be logged into Twitter to get to this address, it happens it's a JSON, and with vLayer you can parse JSON, and in settings.username is your username. So here, so here is a real life code. So this is in our examples. You can download it at any time and play with it. So this allows you to get this screen name. So this is the power of the prover now. This is basically the same code as here, just productized version. So this allows you to prove that you have specific Twitter handle, and in return, mint an NFT with your Twitter handle, right? So this is, think about how much disruption can be done only on an NFT market with that. All right, so web proofs, cryptographic attestation of private data, version 1 coming with JSON precompile, so you can parse JSON, and we're coming with the web browser extension that allows you to fetch data from the web, from your private accounts. There will be more options coming, like you could, for example, do it periodically on the server. So here's an extension. It goes through all the different. You can configure it to go to all the different pages, do all the different steps, and in the last step, it's going to generate a proof. Yep, and that's how you generate, and that's how you configure it. Pretty straightforward. You just create a web proofs, put your own logo there, and just define the steps, where you want to start, what do you expect user to do, and when ready, start to notarize and getting this proof on chain. And last but not least, there are email proofs. So here are some examples of how email proofs can be used. One is wallet email recovery. So imagine you're going to recovery website. Let's say you have a wallet. It must be smart wallet, can be account abstraction, can be Gnosis safe. You say you want to recover your wallet to be controllable with a new address. You hit confirm, and you get an email from the recovery service, and you can reply with a single. It contains all the details about your wallet, and it needs to be matching specific template, and you reply with a single word yes. Hit that send button, boom, your wallet is recovered. And another example, we're gonna go to real world assets again, so that we can compare how web proofs versus email proofs might working for different use cases. So the way it works is, imagine you're managing a real world asset, a stable coin, maybe gold stable coin, and it happens, for example, in the US, that you need to, your custodian who owns your, your securities in his custody, needs to send you periodic updates. And it happens that most of the time it's via email, right? So if you go to this admin panel, this time you're gonna need some kind of extension or plugin or add-on to your email. You find the right email, and in the email from the custodian, you hit generate proof. It's gonna generate a proof, and then you can go to this application and you know the rest of the game, right? So let's look at the code. So here is get wallet address. Sorry, here's get wallet address. It takes as an argument unverified email, which you can verify with a single call of a function, and then you can start querying it with different fields of an email with regular expressions. Here is a more advanced version. We take, so this is specifically trying to recover, so this is a cool example. I told you there's gonna be some disruption with NFT. So this allows you to mint NFT proving you work for a specific company. So what you do, you send an email from your company email stating I wanna mint an NFT, right? So it takes unverified email, the target wallet, which we're gonna use to mint NFT in the verifier. We verify the email, we check it is a domain, whether you're working for Google or Ethereum Foundation or whatever other company you want to prove you're working for. And you check the content of the email is correct, and then you can just return the target wallet along with the information required to mint this NFT. So that's pretty cool. All right, and the interesting thing about email proofs is they are very cryptographically secure because all the emails are already signed by the email servers. So we just need to verify the signature, and our claim on blockchain about email is as secure as your email, which is quite secure, but also, as we know, our emails are not so totally secure. So we should take this into consideration when we're designing our protocols, how secure are our emails. For example, if you want to recover a wallet with a big amount of money in it, maybe it should be just one factor of authentication, not all the factors. But for small amounts of money, it's totally reasonable. And email proofs are coming with a regular expression precompiled for Solidity, so you can parse these emails with regular expressions. All right, so we work very, very hard to make it easy to use. There is still a long way to go, but to start using vLayer, all you need to do is download vLayer app, hit it, and then vLayer init template, and all those examples that I showed you in the code today are available as examples in the code. So you just download them and you can start playing with it, modify them, and see if they works. Right? And we also put a lot of attention to building simple, readable documentation. So there is a book which really makes it easy to start working on it and playing with it. And so maybe some of you already touched the topic of verifiable computations before, and you maybe have seen that people trying to do other things, trying to do this kind of things. So I thought I'm going to mention all the things I'm not going to be talking about. So if you wanted to do verifiable computation, like getting your data from email or web or getting your historical data, in the past, you would need to know a lot about cryptography. So you would probably need to learn some exotic languages used for ZK only. You would probably, along with that, you would need to know things like elliptic curves, fields, and circuits, and what weird things like guess ID mean, and so on. You would need to know about verifiable computations and so. So you would need to know what DKIM records are, or what are storage proofs, or American mountain ranges. So all those things that vLayer completely abstracts from. And we're even getting to a point when you don't really need to understand the deep structure of Ethereum. So you don't need to know what are the different fields of the headers, what are the slots in the smart contracts. Maybe some of you have been to some of those presentations on Devcon, people trying to do multi-chain stuff. And there's like 10-minute introduction to the thing, and then there's 30-minute workshop on working with slots. You don't even need to know the ABI coding, because we basically, whatever prover is returning, you just push to verifier. So there's no need to do any encoding, transcoding of the data between technologies. And there is no need for architecture diagrams. So this is some of the architecture diagrams that you might stumble upon if you tried to work with verifiable data. So by comparison, this is our architecture diagram. And you can start playing with it today. I think I also going to mention, are we doing time? So we have a huge commitment to transparency and explaining how it works. While we make it very easy to work for you, we still want to make sure you're confident that you can trust the code and you can verify yourself our claims. So we publish free reports about web proofs, email proofs, and on-chain proofs, explaining how it works under the hood, explaining what are the considerations if you want to build a protocol on top of that, and a lot of other things needed to gather all the interesting context. And we also published 2 white papers, one specifically about the web, regarding the cryptography behind the web proofs, and one regarding the storage proofs, so the cryptography behind time travel and teleport. So if you want to start hacking, just go to book.vlayer.xyz. Feel free to get in touch with us. And I think that's it from me. We're going to have some real hands-on coding now, right? I'll pass it to Iveta then.
Sure.
Thank you.